Let's continue with the chemical bonding. Just to pick up from where we left last week. We were looking at the periodic table, and we had said that the metals, which are the majority of elements in the periodic table, all these items on the left-hand side of the periodic table, in their elemental form, when we find them as elements, they bond through the metallic bond, whereas the elements that we find on the right-hand side of the periodic table, which are the non-metals, these bond as elements when they are elements through a covalent bond. And the non-metals as elements, they can form either small molecules, like the group of the halogens, small molecules of this type, which are bonded through a covalent bond, if they form molecules, because the noble gases, for example, they don't form molecules, they exist as monatomic gas, because they have complete outer energy levels. And so the elements appear as small molecules with covalent bonds, or they can form, as we saw examples from this group, the group 4 or 14, with the new numerals, where they form these giant covalent networks, like the diamond or a silicon crystal or a germanium crystal, which are like giant molecules. All atoms bond to one another through covalent bonds, and this makes them very strong solids, crystals. They are crystals. We also saw the carbon in its diamond form, this tetrahedral structure, and we also saw carbon in its graphite form, where it forms layers. But now let us continue with a third type of bond, which is the ionic bond. Now, the ionic bond forms when it's not a bond that characterizes elements, how elements form. The ionic bond is exists between metals and non-metals. In other words, if we see in the periodic table again, I shouldn't have taken it away. When we have metals, especially from these first groups that we are interested mostly now in our level, when we have metals bonding with non-metals, usually the bonds there are ionic, this type of bonds. So now the ionic bond does not concern elements, it concerns compounds. We can also have compounds bonded through covalent bonding as well, but now let us talk about the ionic bond. So let us consider metals from these first groups, the group 1 and the group 2 here, which bond with non-metals, especially the halides, but also with oxygen and sulfur in these two groups, in other words. So when we have items from these two groups bonding with items of those two groups, we can expect an ionic bond. So let us see an example between sodium and chlorine, because it's a very famous, here's the sodium and here's the chlorine, which forms the table salt. That is why it's so common, and we can start with this example. So here we have a sodium and a chlorine atom. Here is the sodium, I don't know if you can see it well. Sodium and chlorine atom. Now sodium, it's an element of group 1, it's a metal, and it has 11 electrons and 11 protons. Its atomic number is 11. So in its neutral form, it has 11 electrons, and here we have how these electrons, we can represent them in the energy levels, 2 in the inner energy level, which can take only 2 electrons. Then the next energy level, number 2, can take 8 electrons, and the 11th electron is in the outer energy shell all by itself. The chlorine atom, on the other hand, has 17 electrons altogether when it's neutral, 2 in level number 1, 8 in level number 2, and 7 in the third level, 7. So here, this one is 7 electrons if we count them. So you see the chlorine needs one electron. It needs to pick up one electron to acquire the structure of a noble gas, to complete its energy, its outer energy level. It just needs one, only one. This one has one electron all by itself, so it would need another 7 to complete its energy level. So it's easier for the sodium to give an electron than to take 7, isn't it? So what happens now? This electron here, the lone electron, if a sodium atom comes to close by with a chlorine atom and the two collide, what happens? This electron is attracted by the chlorine, which needs only one electron in any case. So what happens? This electron will go to the chlorine, it's attracted by the chlorine. Here we have this representation. And the sodium remains behind with, stops, in other words, its structure now stops in the second energy level, which is complete with its 8 electrons. The 11th electron has jumped to the chlorine. Now the chlorine here has acquired a structure with 8 electrons in its outer, in the 1, 2, 3 energy level. This is the n equals 3 here, in its outer energy level. And what do we have now? The sodium missing now one electron. Remember that the sodium in its nucleus has 11 protons, 11 protons, and the chlorine has 17 protons. So now that the sodium has lost one electron because it moved to the chlorine, now this appears to be charged. It has a charge and we call it an ion. It has become a charged ion with charge +1, relative charge +1. Why charge +1? Because in its nucleus it has 11 protons and the electrons around it are only 10. That is why it's missing an electron and it has a charge +1. Extra proton, in other words. The chlorine, on the other hand, that has 17 protons in its nucleus, is now surrounded by 18 electrons. It has 18 electrons altogether, which means it also appears to be charged, but now its charge is -1 because it has an extra electron. Nevertheless, apart from the extra electrons or the missing electrons, and apart from the fact that these are two ions now, a positive ion and a negative ion, the electronic shells are complete and they are more stable this way, because remember when we had said that when the energy levels of around the nucleus are complete, these items have less energy and that makes them more stable. In nature there is a law that the less the energy an object or a system has, the more stable it is. It's called the ground state of this object, of these atoms in this case. So these two are now more stable, but now because they are charged, the one has a positive charge, the other one has a negative charge, they are attracted with electrostatic forces because unlike charged objects attract one another. So these two now are attracted and they stay together. They join together as far as they can go, of course, because they're not only attractive forces, they're also repulsive forces between the two atoms because the nuclei repel one another. So they come to a distance which both of them are in equilibrium. Both attractive and repulsive forces are at equilibrium. That means they do not experience any net forces anymore. And the system becomes stable and the two join together, as we said, because of these electrostatic forces that exist between the two. Now, of course, these two do not make a molecule, although we can see that a sodium and a chlorine atom join together and we symbolize it in this sense. These, in truth, do not exist as molecules by themselves. When we have, for example, a little crystal of salt, this crystal of salt does not consist of these molecules. It consists of sodium and chlorine atoms which attract one another in a shape like something like that. I'm sure you have seen this before, perhaps in your book. I should have it somewhere. You see what happens if these green balls, this green, represent they should represent the chlorine ions, and these purple ones should represent the sodium ions. You see, one chlorine is attracted to a sodium and vice versa, of course, through electrostatic forces. But other chlorines are attracted to the same sodium, and so these ions end up arranging themselves in a structure like that, a very orderly structure, as you can see, this crystal lattice, which we have chlorine, sodium interchanging ions, because whatever positive ions attract negative ions and so on. So this is the type of crystals that they form. So you see, it's not these crystals are not made of single molecules. In other words, the sodium, what we call sodium chloride, and we symbolize like that. It's not really, does not exist as a molecule, but this is the smallest unit that we can see here in the crystal, like a formula unit, we can call it, the formula unit, the smallest combination that we can find, those two. And this picture here is the same like that, but we can see more clearly the bonds between the sodium and the chloride ions, how they are arranged. And I want you, I don't know how your electricity is up to this level. I don't know if you have done some electricity and electrostatics especially, but you know, the electrostatic force is an action at the distance force, which means two charged particles, in this case, a chlorine and a sodium ion, do not have to touch one another to interact, to attract one another, which means that every sodium ion in the crystal attracts and is attracted to all other chlorine ions in the crystal, and it's also repelled by all the other sodium ions in the crystal. So the forces are not only, for example, between this ion here and its one neighbor. This ion would interact with all other neighbors in the crystal. So these interactions make the crystal very, very strong. And so the ionic bond is a very strong bond. And I think these are the major points that we can say about the ionic bond. Let's see what it says here. The atoms in sodium chloride, which is the common table salt, are arranged to the smaller spheres. They say the smaller spheres, which are the purple spheres, represent the sodium ions, and the larger spheres represent the chloride ions. Yeah, that is why the larger ones are the green spheres, which are the largest. You might find this a bit strange, because if we look at the periodic table again, if we look in the periodic table, we had said that one of the trends in the periodic table is that the atomic radii decrease as we move along a line, along a period from left to right. They decrease in this direction, we said. Decrease. This was about the atomic radii, However, we see that in our case, we see that the sodium atom, which is the sodium ion, which is represented by the purple little spheres, is smaller than the chloride ion, which is represented by the green spheres. But this is not strange if we think carefully, because remember that the chloride ion has picked up an extra electron from the sodium, and the sodium ion here gave one electron away. So now so the remaining electrons of the sodium now are restricted to the first two energy levels, so it has decreased. You see, the positive ions decrease, are smaller than the atom. So you see, that is why now the sodium ion has decreased, and it looks smaller than the chlorine ion, which has increased. That is why the green spheres here, which are the bigger ones, represent the negative ion, and the smaller spheres are the positive ions. Another thing that we can say is that, actually it's written here, let's go through that. In ionic compounds, like the sodium chloride that we saw now, note that in ionic compounds, they are named with the cation written before the anion. What is the cation in this? The cation is actually the positive ion. It's also called cation. And the anion is another name for the negative ion. Okay, this is the anion. So we see that the cation is written before the anion when we write its unit formula of an ionic compound. So first, in other words, is the metal, because the metal is the cation, and second comes the anion, the negative ion, by convention. All right. So the cation is written before the anion. In other words, the metal first and then the non-metal. And we can recognize ionic compounds because they consist of a metal bonded to a non-metal. Now, why do they bond? Why this electron jumps to the other side? Why the electron, this last electron from sodium jumps to the chloride ion? Why does the chlorine atom picks up this electron? I mean, they do not communicate, they don't talk to each other, they don't have brains. How does it happen? And the reason why is because, we had said in the past that the halides, actually let's look at the periodic table when we discuss this. This, the group 17 elements, the halides, the halogens, are very, very electronegative elements, with the most electronegative element of all being the fluorine atom. If you remember, we had mentioned that when we were talking about trends in the periodic table. So these are very electronegative elements. And electronegative means that they tend to attract pairs of electrons very strongly towards them. And that is why, because chlorine being one very electronegative element, because it can attract electrons towards it, that is why it can pick up this spare electron from the sodium atom, which is not electronegative so much. And that is the reason why the two make, through this arrangement, through chlorine atom, very electronegative, attracts the electron here to that side and ends up with a, we could see it as a common pair. I mean, this electron that goes to that side, we can see it as a common pair of electrons, but no, it's not a common pair of electrons because this electron is attracted so strongly to the chlorine atom that it separates the two. This stays with as a positive ion, missing an electron, and this one stays as a negative ion, having gained an electron. So this common pair of electrons attracted so closely to the chlorine because it is such an electronegative atom that hence we have the formation of the two ions, and then the two ions are attracted because they are two oppositely charged particles. That is the reason why they are attracted. It's not the common pair of electrons that keeps them together. No, it is because this is one charged particle by itself, positively charged, and this is one charged particle by itself, negatively charged, and that is why the two attract one another through electrostatic forces, and not because of shared pair pairs of electrons. And I hope this makes sense to you, but let us see if there are any problems up to now, guys. Please let me know. Do you understand what I'm seeing? Do you understand especially what is the reason, the cause of this attraction that brings the two ions together? Now let us see some examples of ionic compounds. And as you can see in these examples here, look at these first examples are actually a metal. The first parts, of course, are all metals. They're metals from the first and the second group in the periodic table. In other words, from the alkali metals and the alkali earth metals, like calcium, for example. And in the second part are all halogens, if you can see. So in other words, all the metal halides are all ionic compounds, all the metal halides. Metal, because all the metals, you see the metals here, all these are metals, the first part. The metal halides are all ionic compounds because a metal and the halogen is a metal halide with the bond through an ionic bond. But we can also see that metals with oxygen are also tend to be ionic compounds. Not all of them, but many of them, especially from the groups like potassium oxide, for example, or magnesium oxide. These are ionic compounds. And I want us to see in the periodic table again where oxygen is, to remind us. The oxygen and sulfur, you see this group here, group 16, which is next to the halogens, also tends to be quite electronegative in comparison to these metals of that side of the periodic table. Therefore, like alkali metals, for example, with group 16 elements can also tend to form ionic compounds. And not only oxides, but also sulfides. And I hope you remember now where the oxygen and the sulfur is there, so that we can write some more examples. So what other compounds could be ionic compounds? Like we said, with sulfides, with all the metals, like iron sulfide is very common. Iron sulfide, that's an ionic compound. And many other metals, common metals like copper sulfide and silver sulfide, and I don't know, cadmium sulfide, all these are ionic compounds. Whatever the sulfides, in other words, the sulfides are usually in inorganic compounds are ionic compounds. What else can we say here before we change page? That's enough. Silver sulfide, yeah, that's okay. Now, I want us to see, not that one. Let us see those two compounds. Let us see those two compounds. As you can see, here is a carbon connected to 4 hydrogens. This is a methane, this molecule, which is, we can discuss it. We have discussed this before, but let's discuss it again. And if we don't have time, we'll discuss it next week because it's important. And here we have another compound here, which is lithium oxide. Lithium oxide. I want us to discuss those two compounds and see the difference. If we look at the top one, look at this. Carbon has 4 outer electrons. It's part of the group 16. It has 4 outer electrons, very important element. 4 outer electrons, and it needs another 4 to complete its outer level. So by joining to 4 hydrogens, and hydrogen, you know, has just 1 electron because it has an atomic number 1. The electrons from each hydrogen is shared with a carbon. So this happens 4 times. And now what happens is that now the carbon has its 8 electrons that it needs to have a complete structure. And the hydrogen also has a complete structure because it has only one energy level and it's complete. The hydrogen has 2 electrons in its energy level number 1 and it's happy. The carbon is also happy because it has its 8 electrons and it's also complete. So this bond here, this bond between the carbon and the hydrogen is a covalent bond because these 2 electrons are shared, and because both of them, both carbon and hydrogen, in all the hydrogens here, have a complete outer energy shell. So they're both happy, they're both complete. This is a covalent bond. So remember, when the outer energy shells of the participants are complete, this is a covalent bond. But now let's look at the oxygen. And I have this example here because it's my fault. I did it before in the past wrongly. So let us see it here. We have an oxygen now that has, the oxygen has, what is this? 6 outer electrons. 1, 2, 3, 4, 5, 6. Remember, 6 outer electrons. And it needs another 2 to acquire the complete outer level. The lithium now, which is a metal, has 3 electrons altogether, of which it has only one lonely electron in its outer energy shell, which is the n equals 2. So you see this lone electron here, it's easy to go to the oxygen from both sides. So 1 electron from this lithium and another electron from the other lithium join the oxygen, and here we have the result. And now if we notice here, we see the lithium remains with 2 electrons, and but lithium, remember this single electron just was attracted by the oxygen and went to the side of the oxygen. And now the lithium has become an ion because it lost its electron. And it's not that the lithium has a complete outer energy shell. Its second energy shell is not complete here. Remember, the lithium had 2 energy shells, not 1. Yes, the first one seems to be complete, but its second energy level is simply empty. It's not complete. It just gave away its electron. So although this bond here seems to be very similar to this case of the hydrogen and carbon, this is not the same because these electrons are being attracted by oxygen, both of them. And although the oxygen, the lithium has remained as a positive ion, not a complete atom with a complete energy level. It's just an ion that has lost its electron. And this bond is not due to the shared electrons. These electrons are not shared. These electrons are captured by the oxygen, are attracted to the oxygen, and the lithium has remained with missing electrons. So this bond here, it's actually an ionic bond. The outer energy level of the lithium, in other words, is not complete. It just got rid of its electron. But it has this energy level n equals 2, which is empty, but it's not complete. So I want us to see the difference that in a covalent bond, the outer energy level is complete. In the ionic bond, the outer energy level perhaps has been emptied because somebody gave electrons or took electrons. It's not the same bond.